afternoon, this is Schweitzer. We're going to start get close to the end of our videos on gas laws. This particular gas equation is, or I should say this video is looking at this particular equation here, which is called PvnRT. Now PvnRT is commonly referred to as the ideal gas law. Again, what does it mean to be an ideal gas law? An ideal gas would be one where the identity of the particular gas does not matter. So you notice here, these are all the variables. We got pressure, volume, all right, N, which is the number of moles, R, which is the universal gas constant, we'll talk about that in a minute, and temperature. So nowhere here is the identity of the actual gas mentioned. Just like in the combined gas law, you know, there's no actual alright, there's nothing here that talks about the identity of the gases. It doesn't matter because our gases are ideal. Alright, meaning that the identity of the particles don't matter. So here, volume, again, it's pretty simple. These some units here would be liters. This is the most common. You have to have specific units. That's where really is important here. We always use liters. Our pressure can change between atmospheres and millimeters of mercury. That's fine. That's a pretty common one. N is moles. N is moles. And then R, well, temperature has to be Kelvin. You can't get away with that without having Kelvin. And then R, depending on these units or these units, so the only difference is really the atmospheres versus millimeters of mercury. In atmospheres, which is pretty common, is 0.0821. This is on your laminated sheet, so you should find it there if that's something that you have a hard time remembering. If you multiply that times 760, just like atmospheres to 760 is millimeters of mercury, then this is 62.4. So keep in mind that one atmosphere, if you want to convert atmospheres to torr, or millimeters of mercury, Hg, it's 1 to 760. So it's just 760 torr. So torr, millimeter of mercury, the same thing, and these are pretty common units of pressure for for pressure. And these are the two units here we're using for PvnRT. Okay. All right. So let's try an example out. So what do we got here? So in this formula we have PV equals nRT. So common things that we might do with this is solving for a missing variable. This with the formula could be converted over to grams. So that's common as well. Keep in mind that PvnRT is classically used when you're dealing with moles or with grams, and that's when we have to use this. The combined gas law doesn't deal with anything involving moles or grams. Alright, so a typical balloon, helium balloon, has 5 liters, contains how many particles? Okay, so first thing is I'm looking for particles, which is N. Alright, so that's what I'm looking for. PV equals nRT. And I would get in the habit of writing out the formula that you need, rearranging it. So things move diagonally, remember, and do not trap your variable on the bottom, which is not a problem here, but this is just going to move these guys down there. So it's going to be PV over RT equals N. Even after doing this in all of honors chemistry, oh man, kids still screw things up, meaning they grab the wrong R, they grab the wrong T. Those are the two main ones. So a 5-liter balloon contains how many moles of particles? Okay, so these are my conditions. Okay, another sort of shortcut is that at STP, 1 mole of any gas equals 22.4 liters. We might see that here come up in a little bit, and we'll do maybe a little example of that. But here, let's just put in the pressure. I'm putting in 740 here. My volume is 5 liters. My temperature is 25. So I got to convert the 25 plus 273 equals 298. So this is 298. And this is now, because I'm using millimeters of mercury here, this has to be 62.4. And this is going to give me my answer. So I'll take this and go 740 times 5 divided by 62.4 divided by 298 equals 0.198, and it's going to be a unit of moles. A second balloon is blown full of air, N2, to half the volume of the helium balloon. How many moles and particles are in the air balloon? Okay, so in this case, PV over RT, and in this situation, because of the volume is 1/2, then the N is also going to be 1/2. On top, that's all linear proportions. If I double my pressure, I double the number of N. Okay, so keep in mind, PV over RT. The top is linear, the bottom is reciprocal. So if I double my temperature for a given thing, I'd have half the particles. If I double my volume, I get double the particles. If I cut my volume in half, I get half. So the answer is 1/2 of the original number, which was that guy. You could put the numbers in, try it out, you'll see. Student hypothesis, 5 liters balloon is heavier than a 2.5 liter air balloon. So 5 liter balloon is heavier than a 2.5 liter air balloon. Alright, well, heavier, really, I don't know, it's kind of a, I'm not sure I like this question so much. What's that mean exactly? I don't know. Skip that question. Maybe we'll change that one out. Alright, next one. Alright, what is STP? Alright, so STP is 1 atmosphere, okay, and then it is, that's equivalent to 760 millimeters of Hg. 760 parentheses. Okay, and then it's 0 degrees Celsius, which is equivalent to 273 Kelvin. This is what, and also technically 1 molar. 1 mole if we're dealing with liquids and solutions. How many liters of gas will 1 mole occupy? Okay, so we have PV equals nRT. I'm going to solve for V. So V equals nRT over P. N equals 1 mole. R, I'm going to do, let's do atmospheres, so 0.0821. Temperature 273, and then pressure should be 1 atmosphere. And you should get about 22.4 liters. So now we have this connection at STP. I sometimes refer to this as the standard starting place. Then you have 1 mole equals 22.4 liters. Now keep in mind, this is just a shortcut of PvnRT. That's it. So if we're not under STP, then you just got to use PvnRT. But if we're at STP, then you can sometimes just use this link. Alright, what's a partial pressure? So a portion of a pressure total contributed by a specific substance. N total equals N1, N2, N3. So all the particles obviously should add up to equal the total pressure. And therefore, if you look at a particular balloon, that then the volume, so in PV equals nRT, PV equals nRT, for 2 different gases, X and Y, the volume, it's in the same volume, so that's the same. It's in the same area, so the same temperature. R is a constant, so the number of particles that are in the balloon is proportional to the pressure. If you double the number of particles, you would double the pressure. So it's not only proportional, number of particles obviously is proportional to the total particles, but the amount of partial pressures is proportional to the total pressure. So if you have examples, if you had a balloon and it's got half the particles are X and half the particles Y, and the total pressure is just say 1 atmosphere, then this partial pressure of X is 0.5, and this partial pressure of Y is 0.5. But if you have a balloon where, 3 of the particles are X and 1's Y, well, in this situation, you would have 3/4 of the pressure would be due to X. So partial pressure of this guy of X would be 0.75, and the partial pressure of this Y would be 0.25. Notice your partial pressures add up to the total pressure, which is 1. So that's an interesting concept as far as partial pressures are concerned. Partial pressures is kind of like a PvnRT deal. So a balloon has a pressure of 1.2 atmospheres. It contains 0.2 moles of helium and 1 mole of oxygen and 0.5 moles of nitrogen. What's the partial pressure of the nitrogen? So on this situation, I really like this aspect of PvnRT because PV equals nRT has a couple of options here. If you put in the total pressure, then you're just going to solve for the total pressure. Total moles gives you total pressure. But if you do it this way, PV equals nRT, and you put in it only wants the partial pressure of just the nitrogen. So just put in just the moles of just the nitrogen, and you'll get out just the partial pressure of the nitrogen. So let's solve it out here. P equals nRT over V, and N is 0.5, R is 0.0821 because I'm going to use atmospheres. Temperature is going to be, alright, no temperature here, so let's go 273 degrees. I'll add that in there. 273 degrees divided by the volume, which is the whole thing. The volume, pressure, balloon, you got the pressure here. So it wants to know, so that's the total pressure. Okay, so there's a couple ways you could solve this problem. If you had the volume, and if you had the temperature, which I didn't give, okay, is there a way we could solve this problem otherwise? You could plug it in here, let's say it's 5 liters. That's another example of a problem. Then this would go to 5 liters, and you'd solve out for the partial pressure because I put in just the moles of just this guy. Alright? But what you could do otherwise is do it kind of how I did up there. What's your fraction of particles? So there's a thing called mole fraction. Mole fraction is how we would kind of look at this. And mole fraction is very similar to mole percent. It's the moles, let's say the nitrogen, divided by the total moles. It's symbolized by an X, and it has a little n, meaning nitrogen. Okay, so what's my moles of X? It would be moles of nitrogen is 0.5, and then my total moles is 0.2, 1, and 0.5. That's 1.7, I believe. Yep, 1.7. So 1.7. That's now this. If I multiply it times 100, that'd be called the mole percent, and that's what we kind of do sometimes. But this is mole fraction, so it's 0.5 divided by 1.7 would equal 0.24. So 0.24 out of 1, essentially, or 29.4%, 0.294, 94, and that's the mole fraction. So that means when we figure out percentage, it's that percentage of it. It's 29.4% of that. So times 1.2, and we get the times 1.2 equals 0.35 atmospheres. Alright, so 0.35 ATMs. And that is the pressure of just, the partial pressure of just the nitrogen. Of the total 1.2, how much is being contributed by the nitrogen? Alright, and there's our answer. Okay. I did all the other ones too, apparently. Take a look. Alright, so this is kind of what I was getting at before. Alternately, we had calculating pressure. A balloon has 1.2 atmospheres, contains 0.2 moles, and it's 1 liter and 25 degrees. Okay, so now I gave all the information. And I kind of alluded to this earlier, so I'm looking for the pressure P equals nRT over V. The N is going to be, for the nitrogen, is just going to be 0.5, so 0.5, 0.0821 for R. Temperature is 298 in this case. And then it's over the volume, which is 1 liter. Keep in mind, I got that from 225 plus 273 equals my 298 Kelvin. And then you can go ahead and solve this out. Okay? Putting in the moles of just the nitrogen gives you just the total, just the partial pressure of nitrogen. All right. Next one, it looks like we're ending here. Again, review of what we just covered here. PV equals nRT. We probably could have done a few more examples solving for some of these. Essentially, given conditions, solve for the missing piece. Okay. Thank you very much.